All right, this is 6.3% composition and empirical formulas. This is the day where we went to the whiteboards, if you guys remember, and I projected a couple problems for you guys on the board. Now, in general, actually, you guys did really well with this topic, and the reason I think you guys probably did well is because the fact that we did it on the whiteboards, because this is very difficult conceptual problem solving, or at least the second part is. But you guys remembered and you guys stuck with it, and so great job on that. But so, if anything, if you didn't understand it, no worries. Hopefully going through a step-by-step here, it will help you understand. I also gave you guys a handout on a step-by-step of how to do it, and hopefully maybe that helped as well. But regardless, hopefully this video will help you guys as well. There's two topics really here. For one, we first learned how to go from an empirical formula to percent composition. Now, you know, I should put empirical really in parentheses because you guys didn't know that we've been dealing with empirical formulas. I'll explain what that means in a second, but that's our first thing. We learned how to go from empirical formulas to percent compositions, and then we learned how to go from percent compositions to empirical formula, so we learned how to reverse it. But first, yes, what is an empirical formula? Simply put, an empirical formula is a chemical formula that tells us the most simple ratio of atoms in a molecule. So, for example, if we have aluminum and chlorine, AlCl3 would be the empirical formula because it has one Al for every 3 Cls, right? It's telling us that that's the ratio, and this is the most simple ratio. You can't simplify 1 to 3 any more down, right? 1/3, that can't be simplified. However, if you wrote out the formula as Al2Cl6, you'd be correct in some ways, right? Because yes, technically, you know, we know that Al is +3, so if you have 2 times +3, +3 times 2 is +6, right? And then Cl is -1, right? So you have -1 times 6, it'd be -6, right? And so yeah, it balances out, but this would not be the most simple ratio, right? Because 2 to 6 can actually be simplified down to 1 to 3, right? And so this would not be your most simple formula. This would be what we call a molecular formula, because it's not the most simple ratio, and therefore it's we call it the molecular formula, and that's something else entirely. So don't worry about molecular formulas. We're dealing with empirical ratios here. And so if I was to give you an empirical ratio, can you go from an empirical if I give you an empirical formula, would you be able to go to a percent composition? And the answer is yes, of course, because it's very simple. All you have to do in order to do a problem like this is you take your formula and you simply kind of figure out, okay, well, what's the mass of our total of the formula of our substance? What's the total mass? And then just take the percentage for every element. So for example, let's make it easier if we give you an example. Let's say we have SF6, and I ask you, what's the percent composition of SF6, right? So that means, hey, what percent of SF6 is S, and what percent is F? By mass. Okay, that's important to think through. It's by mass. And so here, what you want to first think is, okay, well, what's the total mass of SF6? Well, you can kind of create a mass little table for yourself. If you think through a mass table where it's like, okay, well, you know, what's my substance? You know, we have S, we have F, right? And you can think through, okay, the number of each we have 1 S, we have 6 Fs, and what's the mass of sulfur? The mass of sulfur, if you take a look at the periodic table, is 32.07 AMU, and the mass of fluorine is going to be 19.0 AMU. And so then you can just kind of multiply this. So 1 times 32, you know, this is kind of the total mass of each of these. So the total mass of sulfur in this compound is 32.07. The total mass of fluorine in this compound is going to be 6 times 19, which is 114.0 AMU. And then we can add these together in order to get 146.1 AMU. That's going to be the mass of SF6. Okay, so the mass of SF6, sorry, it's a little bit hard to read. That's SF6 is 146.1. Great, so we have that. Now, how do we use this mass table in order to get the percentages? Well, you can kind of make one more little percent here, right? Basically, the way you're going to get the percentages is you're going to do 32.07, that mass, divided by 146.1 times 100. And then here you'll do 114.0 over 146.0 times 100. And when you do that, you will get the following answer. For fluorine, you're going to get, if you put it into your calculator, you're going to get 78.03%. And for sulfur, you are going to get 21.97%. And then if you add these together, it should add up to 100%, roughly 100%. And that makes sense because, yeah, I mean, if you think about it in terms of a pie chart, right, what we're saying is, okay, what's the mass of SF6, right? Or what's the percentage of SF6? There's only two things in SF6, right? If approximately 78% of it is fluorine, right? Well, then this part is going to be sulfur, right? And in a pie chart, it has to equal to 100, right? So this has to, of course, be equal to 100, right, at the end. And so that's one good way to double check your math there. And so what's the percent composition of SF6? SF6 is 78% fluorine by mass and 21.97% sulfur by mass. The analogy I gave us a lot in class was this idea of muscle, right? Because I know you guys, and you guys are buff and strong, and especially my young men, you guys are extremely, you guys hit the gym and very strong. But also, my ladies, you guys also working hard, I can see. So point is relevant, very relevant for you guys, percent muscle, right? If someone has a very high, like, if someone weighs 100 pounds, right, and they have 80 pounds of muscle, they're going to be 80% muscle by body mass and only 20% body fat. Now, this is being very simple, right? There's technically other things like bones and other stuff, but don't worry about that, right? Let's just pretend humans are only fat and muscle. And therefore, if you are 80% muscle, you're only going to be 20% body fat. And so that's basically what we're doing here, but for our formula, for our substances. So that's empirical formula percent composition. Just take the masses, add them up, and then put them into ratios. However, the second one is a little bit harder. How do you determine a empirical formula from a percent composition? So that's the second part, percent composition to empirical formula. And the way you do this one, and sorry, let me just pull up my little example. Let's say we have a compound, and we see in that compound, once we analyze it, it's iron and oxygen, and we find it to contain 69.94% iron and 30.06% oxygen. Can you find the empirical formula for the substance? Okay, so yeah, how the heck do you do this? What we're basically asking you to do here is we're saying, hey, we have something that's Fe and O, but we don't know how much is Fe and how much is O, so we're going to put variables there. Is it Fe2, O3? Is it Fe1, O5, which would just be FeO5, right? Is it Fe3, O2, right? Like, we don't know, and that's what we're trying to find. That's essentially what this question is asking you. We have to find the ratio of Fe to O. And the way we do that is by determining a mole ratio, okay? Because basically, the mole ratio is going to be the empirical formula, okay? So, mole ratio will tell you empirical formula. Okay, so basically what we have to do is we have to figure out how we have X moles of Fe to Y moles of Oh, that's what we have to find out. Now, how the heck are we going to do that? Well, we're given percent iron and percent oxygen. And, you know, this isn't really useful because, well, in order for us to get to moles, right, we need to either know atoms or grams. And we're given percentages, and so that's not very helpful. Now, I'll give you guys a hint, actually. It is, you know, we're going to go from grams, not going to be from atoms to get to moles. And again, remember, we did this in 6.1, right? So we know how to go from, or sorry, 6.2. So we know how to go from grams to moles. But the question is, how do we go from percent to grams then to moles? That's what we don't understand. And here's the trick. What you need to do is you need to assume a 100-gram sample. If you do that, you're easily going to be able to get grams, and I'll explain that to you in a second. And then to go from grams to moles, you're going to need to use molar mass, right? And again, we learned how to do that in 6.2, so take a look at that video if you don't understand that. Okay, why do I say assume a 100-gram sample? Well, I'm not going to write this out because it'd be a lot to write out, but just try to follow along with my logic here. If you have a substance that's NaCl, okay? What's the ratio of Na to Cl in an NaCl? Right? In NaCl, the ratio of Na to Cl is 1:1, right? And actually, sorry, I'll write some stuff. Right, NaCl, no matter what, is always 1 Na to 1 Cl. Does it matter if you have 5 grams of NaCl, or 10 grams, or 20 grams, or 50 grams? Will it change our ratio of NAs to Cls? No, right? The answer is no. It's not going to change your ratio of NAs to Cls. No matter what, no matter how many grams of NaCl you have, you will always have the same ratio of NAs to Cls, right? And so it doesn't matter. So because it doesn't matter how much NaCl you have, it also doesn't matter here, right? It doesn't matter how much Fe and O we have, right? We said we have a compound, so we have like a sample of that compound. Does it matter how much of that compound we have? Does it matter if we have 5 grams, 10 grams, 20 grams, 50 grams, 70 grams, 1,000 grams? No, right? No matter what. It's a mixture of iron and oxygen in the same ratio. And so it's not going to matter how much of the sample you have. So let's try to make our lives easy. And let's say 100 grams, okay? Assume a 100-gram sample, because here's the thing. So let me just write that. Does it matter? So if it doesn't matter how big the sample is, so we assume 100 grams of our mystery FeXOY, right? So if we assume we have 100 grams of it, okay, if we have 100 grams of this substance, right? And we said, right, we had found that 69.94% of it is iron, right? 69.94% as a decimal, right, is 0.6994. If 0.6994 of 100 grams is iron, then how much iron do you have? You have 69.94 grams of iron, right? And, you know, again, if we have a 100-gram sample and 30% of it is oxygen, how many grams is oxygen? It's 30 grams, right? And so now look, we have grams. And we can then use those grams, right, in order to go to moles. And so by doing this 100-gram sample assumption, we basically are able to get some number of grams because it doesn't matter, right? It doesn't matter how many grams you have, right? What we really need, though, is to have those grams and then to be able to go to moles via molar mass. And so we do this assumption, we get grams, and now we can work with these grams, again, knowing that it doesn't matter how many grams you have, right, because the ratio is going to be the same. So now that you have that, you can go to your second step. So that was kind of step 1. And now step 2, you can go from convert grams to moles. And so we can go from 69.94 grams of Fe and 30.06 grams of O. And we can get moles of Fe and moles of O. How do we do that? Via molar mass, right? You just take a look at the periodic table and you get the their molar masses. The molar mass of Fe is 5.85 grams of Fe per 1 mole of Fe. And you get this as your answer. And you have moles of oxygen, grams of oxygen. Very satisfying. And yeah, now you have moles of oxygen. Wonderful. So now we have these moles. So now step 3 is construct the most simple whole number ratio. And so how do we do that? Well, right here we have 1.252 moles of Fe for every 1.879 moles of O. Now, you might be tempted to be like, okay, that means that we have, right, 1.252 Fe for every 1.879 O's, and that's our formula. There you go. We're ready to go. You can totally turn off this video and we'd be all set. Except please don't do that. There's a couple more minutes, and the reason why, right, because we can't do that, right? Because yeah, I mean, who writes their formulas like that? You've never seen a formula like that, right? So that's why we need to make the most simple whole number ratio. Now, how the heck do we do that? How do we turn these into whole numbers? Well, here's the trick. You can do this in a variety of ways, actually, but here's what I'd recommend. Take the smaller of the two and divide both sides by that. Because if you do that, then at least, what's anything divided by itself? It's just going to be 1. Right? And then what's this divided by this? Well, that's not going to be 1, but it's actually going to be something kind of nice. And if it's not nice, we can work with it. So if you were to do that, you would get 1.5 moles of O. Now, you might be saying, wait, that's not nice at all. But it actually is, because 1.5 isn't nice. However, what if I took all of this and I multiplied it by 2? We would get 2 moles of Fe for every 3 moles of O. And oh, look, wait, isn't that nice? 2 moles of Fe to every 3 moles of O? Wow, wonderful. So now, right, we have our ratio. What we're going to get is Fe2O3. That's our formula. Is that the most simple ratio? Well, yeah. Can you make 2 over 3 any simpler? No, you can't, right? 2 over 3 is the most simple ratio, right? Or technically, we could also flip it over and make it 3 over 2, right? But that's the most simple. You can't make it any more simple. Is it a whole number? Yes, 2 and 3 are both whole numbers, right? And so what I call this is scaling up. At the end, you're going to need to scale up, potentially, right? If it's not a whole number by this point after you divide both sides by the smaller one, you might need to scale up. Now, my regular chemistry students, I would never have you scale up because, well, math. So we'll stop there. But AS, this is a challenge, and you can do this. And so basically, again, if you're regular, you can stop here. But for AS, for scaling up, right, what I'd recommend is, you could guess and check, to be like, okay, times 2, times 3, times 4, see what works. But what I'd recommend is to think of numbers in terms of their, fractions and mixed ratios. So for example, let's say we had gotten to the end and I had gotten 1 Fe for every 2.33, actually let's make it 1.33. 1.33 oxygens. Now, some of you can see it already, right? You'd be like, oh, well, you can multiply it by 3. But if you didn't get that, right, how I want you to think about it is, okay, what's 1.33? Well, 1.33, right, is 1 and 33 over 100, right? That's another way of writing it. But 33 over 100, right, that's really just 3 over 10, approximately, or it's actually 1/3, right? And if you don't know that, just put in your calculator, right? 33 divided by 100. Right, I guess just calculator doesn't do it. Let's see, can I? No, actually this calculator doesn't do it. But a lot of calculators, they'll just turn it into a nice ratio for you. Let's see, does this one do it? 33? I don't think so. Yeah, no, this one's not a great one. Technically, you can actually go into its types here and put it in. But don't worry, you don't even need that because, again, you're AS in math and you're good at math. So, right, 33 over 100 is just 1 1/3. Now, 1 1/3, that's actually 3 times 1 plus 1. That's really just 4 over 3. And so our ratio here is 1 FE to 4 over 3 O's. How do we get rid of the 3 here? Well, if you multiply by 3, right, you'll get 3 FE for every 4 O's. And so the ratio here would be 3 to 4, right? And so basically with scaling up, what I recommend is to put your number in terms of a fraction and then turn it into a mixed number. And then you can just multiply by the divisor here. So yeah, that's how I would do it. But yeah, all that to say, this is how we do, how we go from a percentage to a empirical formula. What you do is you assume 100 grams, convert grams to moles, and then construct the most simple whole number ratio of varying degrees of difficulty depending on the chemistry you're in. So hope that helps. Hope that was helpful. Let me know if you have any other questions. Hopefully we'll see you soon.